Welcome everyone to the seminar series of our technical committee on model-based optimization for robotics. For those of you who don't know me, I'm one of the co-chairs of the technical committee. My name is Yue. And today we welcome our speaker, Alessandro Saccon. I will first briefly introduce our speaker and then leave the floor to him to take over. So Alessandro is an associate professor in nonlinear control and robotics at the mechanical engineering department of the Eindhoven University of Technology. His research interests are focused on modeling, analysis, and control of complex and highly dynamic robotic and mechatronic systems. His current research efforts are directed toward the development and validation of innovative control strategies for robotic systems with multiple intermittent dynamic contexts, with application in the field of dynamic robot manipulation and locomotion. Within this context, he's coordinating the Horizon 2020 European project, IAM, or IM, I don't know, you will probably say it better, focusing on impact-aware manipulation for logistics applications. So Alessandro today is going to give us the talk on impact-aware manipulation, exploiting intentional collisions to speed up task execution. The floor is yours.
Thank you very much, you, for the introduction. And yeah, good morning, good afternoon, and good evening to everyone. Thanks for having found some time for this hour together. I want to start, of course, by thanking the organizer of the event for the kind invitation introduction, and to present the research we conduct here at the TUE. Yeah, indeed. So the talk will be on impact-aware manipulation, and we'll tell in a second what I mean with this. Let's see if I can go. Yeah, a bit of introduction. Where are we, or where am I? So we are in Europe, north of Europe, in the Netherlands, in Eindhoven, which is in the south. So you probably heard about Amsterdam, Rotterdam, and this is pretty known. Eindhoven is in the south, and is the hometown of Philips. Originally, so that's a company international that you probably heard. That also started the whole university back like 50 years ago, and then out of this a whole group of companies and also other activities spun out of this. So a few companies that you might heard about is ASML and XP, and then this is all essentially high-tech mechatronic industry. But then there's also quite some automotive activity with trucks and stuff, and also logistics, which is a big company, Van der Lande, that is doing, for example, automation in airports, or parcel and warehousing. So we are actually in this region, so collaborating with all this area, and the area around here is also called the Brainport. So if you're curious, you can also double check. The TUE looks like the picture you see on the right, and then Eindhoven city and downtown. If you never saw it, it's like the picture right there. So this is a high-tech area. It's also interesting to know, that this is an area where also Van Gogh was living at the beginning of his life. So if you're close by, there's a place called Noonen, 6 kilometers from the TUE. You can still see some buildings, some things, and this is a famous painting from about 150 years ago. And it's interesting to see that the area developed from essentially extremely poor area with almost no technology to what it is now, that is really vibrant and international. So what are we doing here at the TUE in terms of robotics? We probably know that we are also on soccer competition, so we have activities on RoboCup. RoboCup will also be organized here in Eindhoven this year. So there's a lot of my colleagues working on multi-robot collaboration and on strategy. How do you make a system also collaborating with humans? There will be I think first match with humans this year. But my focus here is more the TUE is really on dynamic manipulation, and the idea is how we can actually exploit collisions, intentional collision, to make things happen faster, and or do things that are not possible. I mean, in this case, like reaching a certain destination that is out of reach, out of the workspace of the robot. This is a demonstration that we did of the type of technology we are developing for a case of robot tossing, and this idea of speeding up the process. I will say a little bit more later about this. Let me see if I can click. Okay, a bit of my journey, a bit of background of myself. I mean, I'm actually Italian. I studied in Padua in the northeast of Italy. I'm a computer engineer by background. I did a PhD in system and control. I was actually back then working on virtual motorcycle riding. So that there was a company, Ducati Corsa, that was trying to get simulators or lap time simulators to understand how to better predict the behavior. So then I essentially moved from system control and computer engineering background to more mechanics, I would say. And then we had collaboration with companies that are producing things like Adams, a multi-body simulator. And in this period, I spent quite some time also in the US, about 1 year, where it was mostly working on numerical optimization, linear control, maneuver regulation, path following. And through this journey, then I worked a bit in Ducati Corsa in collaboration, developing tools for racing motorcycle. But at a certain point, I said, okay, I actually prefer staying in academia, and then essentially I move on, to starting going a bit around. I spent a few months in Caltech, looking more at Lie group theory, geometry, geometric mechanics. I did a postdoc in Lisbon, again on optimization, and I started moving towards robotics. I spent some time in ANU in Australia, and finally I landed at about 10 years ago in the Netherlands, where I really started looking at more robotics and impact-aware manipulation and smooth mechanics. So this is more or less on my journey, just to give you a bit of a background. So I actually spent a bit from electrical engineering to computer engineering, computer science, and mechanical engineering. And finally, a couple of years ago, I also spent some time in Munich, 3 months. It was interesting to be in the group of Sami Adadin, but also visiting other groups in there, also DLR close by. So this is more or less my journey, just to give you a bit of background. So, and when I landed at the TUE, there were people here looking at problems how to stabilize motion where there are impacts, and I started, more from the mechatronics perspective, and I started looking at this problem, and also understanding that this could be also relevant for robotics. So when I say impact-aware manipulation, I'm referring to this type of motion. This is really, what operators or human operators are asked to do when removing objects from a truck unloading. Sometimes you see these videos where all the nice boxes are aligned, and you have a nice robot that goes and picks it up. But this is typically the condition that people have to work with. And that there's a question of, hey, how do you make machines being able to deal with this? To estimate even the weight of things as you pick it up, exploiting all the contact. But you see that many times, you make interaction with the body. The objects are heavy. So that's, one of the motivations is how do you make a machine behave this way? And the reason is, there are many tasks, especially in logistics, and here in the area we have companies like this that are looking at automation. How can we perform these operations that are needed, but sometimes there are not enough people because to perform. And also this type of operation can be demanding for the whole body. Another video related to this aspect, is like also one of the things that I found in YouTube, but also motivating many years ago to see, because people will say, yeah, there's no robot can do this, right? So this is again an example of how incredible human or we are in handling object relatively heavy. This is probably half a kilo, 1 kilo, so it's 2 pounds, and then still being able to do by manual manipulation, understanding what happens when these heavy packages interact with our hands, and how we quickly also can fill in those. So this was a bit of a motivation, and the things that I'm also trying to understand. Okay, how can we have machines doing this? And of course, hardware is getting ready, in the sense that this is a very well-known video from Boston Dynamics, showing that up to a certain point, I would say 10 years ago, 15 years ago, people will say, okay, don't have a robot impacting, don't try all costs to have collision avoidance. And in many situations, this is still relevant, and indeed you should not always want to impact. But there are the hardware now is getting more and more capable also of allowing robots to jump, to run. And there's a lot of literature that has and research that has been done on, I would say, on locomotion, both for bipedal and quadrupeds. And my interest is also looking at more at the manipulation part, okay? Because I mean, there are no gates, there are other things that are interesting. So that's the motivation. Hardware is getting ready, and okay, how can we make this more how to say, a common technology that is available. So there's also, you can probably see that there's a rise of commercially available dual arm manipulators out there. So half humanoids, just arms with torso, and also full humanoids. Last year was just incredible, right? For humanoids, you have this Optimus, for anyone, a Figure, Phoenix, and way more. And I just put there a few, and you see the different type of robots that are compliant and drivable with joints, and they are really meant to physically interact with the environment. So there's maybe a little bit of a hype in the expectation that these robots will be able to do everything like we do in a few years. I don't know if that will be true, so we'll see if this how it will evolve. Anyways, it's very exciting period in time, where incredible hardware is getting available even at commercial level, not just in research centers. And there's all kind of things happening also for perception to really understand where objects are in the world, and so then the question is how can we perform this action again at regular speeds. But then for me, it's also interesting, okay, how can we speed it up? How can we really bump into things on purpose? And how can we then still make these motions somehow robust? Because you can have a plan, but of course it will never go as especially if you have impacts, it will never go as expected. So what to do in that case? Good. So impact-aware robotics, we are, like I said, as humans, capable of the dynamic interacting with the environment, with objects, with the ground, with all the walls around us. We do it every day when we run or jump, and so for locomotion, but also when we grab and toss objects for manipulation. And robots are not yet, but they are definitely catching up, or in the sense that people are developing better and better hardware every year. So then there's essentially this emerging field that is really focused on exploiting contact and also exploiting intentional collision. And so that this is what I mean with impact-aware robotics, is a term that we sort of coined in the last year. And also there's a special collection, IEEE, Transaction Robotics, with other colleagues in the US and here in Europe. And some papers will come out in the coming months. We had like 40 submission to this special collection, and then we are revising probably 10 papers or about that number will make it through. You will hear more, but the idea is like, okay, well, why should you care? But why is this relevant? Well, the things that you see, the plot on top is really this idea of if I'm moving and I'm picking up an object, currently, and also the time you really have to stop. So you have to decelerate over time. The velocity goes from a certain level to 0. You pick up the object and then you accelerate again, right? Why are we doing this? Well, we do it because it's known how to do. And this is the way that, for example, Delta robot on conveyor belts, and pick and place are really doing things super fast, low inertia, but at the moment of making contact, they essentially the velocity of the end effector is aligned with the velocity of the conveyor. But it's definitely not ideal in terms of time and energy consumption, because in terms of energy, you always have to decelerate and accelerate. So, and here's an example that, if you see on the bottom, if you don't need to stop as you pick up an object, you will have maybe a little bump, or depending on the momentum or the weight of the object, you will have a decrease in speed because you have to pick up an object. But time can, in certain situations, especially if you think of going from right to left and picking something in the middle, the time can be shortened of half. This is a simple computation, but the thing is that you don't have to decelerate and accelerate, so this in principle can reduce time. It's true you need the right hardware, so that's something that is still in development. But the other point is, like, even having the whole hardware is not fully clear how to do all those things in a robust way. So this is where we are essentially focusing. So what are the challenges? So indeed, this is the standard practice, right? So free motion and establishing contact at zero speed. And this is, like I said, is a bit limiting and restrictive. And why don't we have the whole, something motion like similar to what we do? Well, the point is that you have to rethink many parts in order to be able to do this. And from modeling, okay, what kind of models I'm going to use for this? From planning, learning. If you execute certain motion, yeah, the learning with impact is different from learning of when you assume the transition of the zero speed. Controlling estimation. So we are essentially missing several things that there has to be also a holistic framework to be put all together. So that's the vision that I have here, but there's also many other, I think, researchers worldwide and maybe with completely different approaches that we are trying to create this type of technology. And for me, it's really trying to really show it on real users cases. And because the industry around here, for me, makes a lot of sense to focus and discuss with focusing on application on logistics. But the technology is totally general in principle. It could be applied for all kind of type of manipulation. And there's a lot of things for sure also on locomotion. So the type of motion we target, this is something that indeed give an idea. So here's a two-alarm system we have the lab, and then that's, this is a couple of kilos that you want to lift. And then this is the type of motion we now execute and we can perform with the type of controller. And there are sort of robust even to the fact that, we plan the motion where to pick up the two boxes that you see in the middle, even if they are in the center, but even if you displace them a few centimeters, you still can execute these things with relatively high gains in torque control mode, right? So that's more or less what you end up. I don't know if the audio is off, I think, but okay, you will hear. Let's see again. Yeah, this type of motion we target. And the moment you impact, you don't only have an impact in the normal direction, but also tangential. So you really lift it up. And the question is, okay, how we manage to do this and what are the challenges? And I'm going to explain a little bit, our way of thinking and the type of research and line that we've developed in the last, I would say, 10 years. So what are the challenges, missing parts? One thing is relatively important. We are conducting research, but there's plenty of things still to do. Is really having validating impact models for that can predict what happens. So if you want to interact dynamically with the environment, you need to have some prior information, for example, about the object you're going to lift up. So you're not going to lift up a very heavy box without knowing its weight. Because the way that your body reacts to it when you lift it up, it really depends on what is inside of the box, what is the weight, where the center of mass is, so on and so forth. So in general, if you have to pick up a lot of objects, yeah, maybe the first one you handle really shortly, then okay, you learn a bit of is there a dynamics inside? Is there something? What is the weight? And then as you know that the objects are always the same, you start being fast and fast. And this is, by the way, one of the reasons why people get injuries in maybe also in logistics centers, because you after a while you make assumption about the weight of objects, but the moment that the weight is completely off, then you have really a problem because you are prepared to handle an object of a certain mass, but then the mass is completely different, and this can create problems typically on the back. But in any case, we need in complex scenarios to have this type of model because most of impact-aware control is predictive. So you should have an idea of what is going to happen, and then somehow the controller is built around this I would say feed-forward motion to make sure that the control is not disturbing the natural dynamics of the system. But there's quite a lot of things to do still on predicting and understanding which type of models, because reality is flexible. You have all kind of effects. The robots are flexible, the objects are flexible, and up to now we are using essentially, if you do model-based, essentially rigid robots. So, if you do modeling and planning with rigid robot and then do experiments with impacts where there are flexibility, you will see oscillations that will never be in the simulation. So, how to compare? So we are looking at this. I will say something about this later on. But there's plenty of things to still do, also to develop software to be really able to use these things online when a robot is executing the motion. So once you have these predictive models, you probably want to have controllers that are robust to the time mismatch, because you can plan to touch and grab something with two hands at the same time in a certain moment, but there are perception error, there are mismatch in execution. You will never, especially if you have multiple contacts at the same time. Yeah, you might have planned to touch things simultaneously, but it will never happen. So, and this is why interesting what happens in that case. And a controller have to be very, they have to do something clever not to destabilize this type of motion. And this is one of the things I will speak more the most during this hour. The things that if I'm going to be fast, then it's better that I realize very quickly that something is going off. So if you start running and you think there's a lot of grip on the ground, but then it's sort of cold and it's icy, and then there's not much grip. It's very important you realize very quickly. And so this is something that we call also in the project coordinating aim-aware collision monitoring. So our impacts are supposed to happen, but are the outcome of these impacts what we had expected? Yes or no? And based on this, you should activate reflexes and behave differently. And also, there's a whole question of planning. How do I plan motions where I have impacts? So that's another. So how should I bump into things to get what I want? And we are really good in understanding this. If we want to push a heavy box, so where should I put my hand, in which speed and which direction should I go in order to get something happening? And then there's also the whole question: if we want to demonstrate to the robots certain motions, what kind of information should we expect for then sending this to a controller that can be robust to mismatch or incorrect positioning of object when you repeat the motion. And in general, you will need also to have a whole software stack put all together. We are also working a little bit on this to make sure that you have all these tools in one place. So the hardware is becoming available, like I said. Not all the robots that are out there are really suitable for this. But there's still ample space for improvement on hardware. And in any case, my focus in the last years has really been on this theoretical aspect, software aspect, and validation. In this talk, it's 1 hour. So like I said, it's about 10 years I'm working on this kind of ideas, but I will mostly talk about the control to be robust to this type of mismatch, and a little bit on impact modeling and a bit on how we, for example, extract some information from a demonstrated trajectory in case you don't have a planner to make it robust. So what we have developed here at TUE is we call it a reference spreading. It's a control strategy, and that is really we started in 2014. And I'll give you an idea in a second what I mean with this. So it started, like I said, in 2014, more or less when I arrived here. People were looking at electronic system, and you want to execute a certain motion. This is something we built. Is what we call an actuated rebounded pendulum. So it's a pendulum that has a stop, a mechanical stop, and whenever the pendulum impact the mechanical stop, it bounce back, right? So it's a direct drive robot, and that is meant to have these partially elastic impacts. So if you let it go, if you apply a constant torque to it, then what you will see is that the position sort of the pendulum goes towards a zero. Zero is the position of the stop. Then it bounces back. And after a while, because you lose energy, sort of tend to stabilize. And if you look at the velocity, then you see that there are really crisp jumps in the velocity, and in this case, you apply a constant torque. So the idea that, okay, suppose that this is a natural motion of the system, and these impacts are related to somehow related to what the system is actually doing. How to stabilize it? Yeah, if you try to do standard PD controller with feed-forward, what you will get is typically something like this. Oh, by the way, the assumption here is that the impact takes 0 time, which depends really on the sampling time. So if this is like 100 hertz, 500 hertz with this type of system, you really see that the things is discontinuous. In reality, of course, it is not. If you start sampling at 10 kilohertz or things like this, you really see that the velocity is continually changing from minus in this case was meters per second or radius per second to +4. But depending really on the sampling time, these impacts can really become discontinuous. So our way of thinking at least is try to abstract away, not really modeling the whole deformation, also because it's impossible that you will be able to figure out the spring and damping characteristic of all the system depending on the configuration. That's something that's possible maybe for one particular configuration, but in general it's not. So we take the assumption that essentially we can model this as a non-smooth or hybrid system. And then, like I said, this depends really on the sampling time. But like I said, if you start applying a standard PD controller, like a feed-forward plus feedback, that's the kind of things you encounter at the moment you start, not exactly on the reference. So in this case, the red curve, you start a little bit in a different position. And what happens is that because you started a little bit closer to the boundary, you will bounce already. But if you are essentially just following the reference as you that was given this blue curve, the reference still need to have a jump. So the controller is trying again to make the system jump again, right? So you have a really weird behavior like the ones that I show here, especially with low gains, that the tracking is extremely poor. And ideally you would like to get something like this, right? And it bounces, and then you start following the new envelope, so on and so forth, right? This is nice. But how do you get this? Because it's definitely not what you get if you apply a standard tracking controller that usually are not really meant to track trajectory with impacts. So the idea was pretty simple back then, but from this simple idea we proceed up to the point we can execute this on dual arm system and grab boxes with essentially no problem in the last year. And here it sort of shows what is the issue. If you have a reference trajectory, in this case is red, and then you have a common, the executed motion, you see that if you take the difference between these two trajectories, then you will have this kind of a peaking effect, because there is always a time mismatch between the nominal impact time tau d and the actual one tau 1. Right, so the idea that we started to pursue is really, okay, instead of only having one reference about the nominal impact time, try to have more than one. Okay, so like you see in this picture here, these things are a little bit extended. So the way it's extended, it really depends on the application, but the core idea is like we have essentially more than one reference in a neighborhood of the nominal impact time. And then if you have this notion, then you can define the error based on the fact that you have experienced the impact or not already. So in this case, the error is between these two curves that I'm highlighting up to the point, where an impact is detected. And when an impact is detected, then you will actually start following the other and define this as the error. And the result is that, you get completely different type of error definition. And this simple trick, allow you to get this type of behavior that I was showing before, with not even changing the gains. Okay, so with these same gains and new error definition, you have the behavior. And so one question is like, okay, what do you get? Where is these things coming from? And I think it was really coming from the idea of trying to do planning for motions with impacts, and then trying to do sensitivity analysis. And if you've done this type of things, it's like, okay, I suppose you have a system like this. There's a jump at a certain time, and you try to perturb the trajectory, and then the impact will occur at a different moment. And it turns out that you can actually try to build a first order approximation of this system. And there are beautiful results even from, I think, a former PhD advisor of you and Katja Mombauer. Then you can actually compute an equivalent system that always jump at the nominal time. And this relationship between the two is actually what people also refer to the saltation metrics. And I think it's interesting that if you look at the theoretical analysis of and derivation, you actually end up having to define a new type of trajectory here that I'm talking like that I'm indicating here with the alpha bar. So you still need this extension in the proof in order to really understand and build this construction. So it turned out that, you know, from this analysis, naturally these trajectories are occurring. And then essentially 10 years ago, I sort of stopped and I said, hey, but these things can also be used in control. It's not really just for motion planning. So I mean, the result is that you can indeed come up with what is called a time trigger linearization. You can get this gain here, G, that is this saltation matrix. And I mean, now this is more for impressionism. There's no time to go into the details. But the thing is that you can use this type of system, at least if you have single impacts, to study stability or control in a neighborhood. But the main take here was this idea that you can actually have more than one reference trajectory about a nominal impact time. We went through, and there's quite some publication. I'll put it just here for the reference in the future if you want to know more about this part. And you know, then you know, we did a lot of experiments, and also interesting. Again, this is related to this impact map. You know, you need to have these pre-impact velocity, post-impact velocity type of you know, models, and then you can use this to generate references. So this is the part of the prediction I was talking about. And we demonstrated that you can take this type of trajectories. You have maybe a desired motion. In this case, is a little bit more complicated than the one that I showed you before. With also the torque that is different. So this is the light blue. You can do this type of extension. And here is like, okay, if I use the tree controller with the different gains, exactly, this is experimental work. You see that, you know, for the low gains, you really have poor tracking, this behavior that I was mentioning before. If you increase the gains, then somehow you converge, but usually you have really high peak because essentially there is always this mismatch between the impact time and the nominal impact time, and because you have really high gains, this creates peaks. And we show that, you know, if we use this idea of extension with the same gains, we get convergence to the trajectory. That is fine. And here you still see that you have these peaks, and then this is interesting to do experiments to understand that if you use this was the, I think the, yeah, this is the animation. Yeah, that's how it looked like, just to give an idea of how this trajectory looked like. But we notice essentially that if you use encoders to compute velocity, of course, the velocity estimation is very good whenever there are not impacts. But if you have impacts, then you should have a filter that changes its bandwidth in order to estimate better the velocity. So that's something that we developed with the students in the past, at least for this case, to show that once you then actually use this type of jump aware velocity filter, then you know what you get experimental is pretty close to what is is shown in simulation. Essentially, you can always track with different gains this trajectory. Essentially, also not having really any spike in the torque due to this peaking effect that I was describing before. And you know, having these peak effects can be detrimental for the hardware. So that's also why we were interested in looking at this. And this is something important also for robotics. Right. So then back then, once this was clear, we had some good connection with people in Italy in the group of back then of Francesco Nori, that is now in DeepMind, but now it's Daniele Pucci. So we were sort of saying, okay, can we apply this to robots? And so then you have a robot have to bump or do some sort of exercise against a wall, a humanoid, and then we show, okay, we can use this idea to stabilize this type of motions, and then showing that indeed, that you can, even if you have a desired motion that in this case is green and a solid one is closed loop, you start at a different moment, you can really have this convergence even if you have this mismatch. And this was also employing a QP controller for doing the balancing of the robot. So we showed that back then, a few years back, that this idea could be relatively easily applied to real humanoids and systems. So that then the thesis of my former students finished in 2018, and where all these kind of things are described. And then after a few years after that, we got funded from the European Union to continue. So then involved also other colleagues, all the Bilal, Abdel Kadar, Sami Radin, as academics. You probably know them all well. And some companies are active in logistics. And then company Franca Mica, now Franca Robotics, of course, and then Algorix is a company doing things in physics simulation in Sweden. In particular, this company for making sure to simulate complex simulations. The project will end in March of this year. And in the project, we are focused on tossing, on boxing, and grabbing scenarios, all things that comes from real logistics use cases. So people want to speed up this in-feed process, taking object and put it on conveyor. People want to try to have bean-to-bean motions where you use contact and impacts to speed up the filling and also the filling rate of the stones. And for the grabbing scenario, is more a dual arm manipulation where you do the palletization. We have a lab here where we test especially the first two use cases. I'm not going to discuss this much today because of sake of time, but I will focus more on this dual arm manipulation part. And just the thing that we are doing here at TUE, because the other partners that I mentioned, they're also doing fantastic work there. So I mean, you can check and look at the publication on the website on what they are doing here. I'm just representing what we do at the TUE. This is an example of the type of motion I was telling you. I mean, where people grab and put objects and dual arm grabbing, and you see that the operators will pick up more than one object at the same time, or will make it slide. But this is the type of motion we would like to automate. And the group in Dakar was trying to put their type of control strategy with the QP, also to show a humanoid performing the same motion. This is not really using the things that I'm going to discuss, but it's still interesting to see that having robots performing this type of motion. And here at TUE, we are. I will just show this. There was an Automatica, showing this idea that if the animation works, just to show that we can perform even with the dual arm system, fairly complicated and interesting motions. And this will be in this case just contact rich type of manipulation. But the part that is interesting for this talk is not really this manipulation part here. Is really one of the last part where you will see that after placing a few boxes on top of each other, you can actually go to some flipping and rotating, and then the question is how would you stabilize in general this type of motion, like the one this type of motion that I'm mentioning here. And of course, this is the reference here is teleoperated. I mean, they should not be a surprise for most of you. But the question is, once you have this type of motion, how you make them robust, how you stabilize them. And this is what I'm going to discuss in the last, I would say, 15 minutes that are remaining. So one of the interesting things is really that if you want to, for example, have a robot making a box slide on the table very quickly. What happens is that this is a sort of a surface contact. So, and ideally you think, okay, the box will just touch with all corners on the table at the same time and will start sliding. So there's only one impact, right? And this type of motion a bit everywhere, dual arm grabbing. And so your intention is always to do this, but the point is that this will essentially never happen in practice. So you can have this target, but then you want to make sure that even if you have misalignment and therefore all kind of series of spurious impact, that the dynamics is still stabilized. And what the problem is that is, the thing is that once you have this spurious impact, in this case, that one impact is the nominal one, and in the simulation, and then the other one is this spurious one where you have an initial condition that is not as you wanted. You can have really sudden changes in the for example, in the angular velocity. So think about the box, you're holding a box and you're making it slide on a table. Yeah, the reference will say, oh, the speed, the angular speed of the box is 0 before and should be 0 afterwards. But if you have this spurious impacts, then suddenly the angular velocity can become extremely large. And this actually, the thing is that in the dynamics of the system naturally will try to push it back to that level. So if you would just use an impedance controller with high gains, this is actually problematic because of the fact that you are trying to reduce that speed, but actually that the angular velocity is actually helping to do the stabilization. Okay. And so we actually show that it's actually possible to even study the sensitivity of these type of trajectories. There's a paper we wrote a few years back in showing that again, if you have a nominal motion that is like this blue one, and then you execute a motion where you have all these kind of spurious impacts, as I'm indicating with the laser pointer, you can still find an approximation that jumps at the nominal time and can still represent the perturbed motion away from this spurious part. Okay, and so similar to this saltation matrix, it's actually possible to build a representation that tells you what the system will do. The interesting result back then was that we show that this gain now is not anymore linear; it's only piecewise linear. So it's actually a positive homogeneous map. That also tells you a bit of the fact that if you're trying to do optimization, you're trying to find trajectories. Well, we are in a totally uncharted territory because the system is not linear. So try to compute gradient descent. It's not really possible if you really are mathematically, if you want to be mathematically correct. But in any case, again, I don't have the time, of course, of checking all this math. If you're curious, you can look at the paper we wrote back then. But in any case, this suggested a way again on how to control the system in this case, and this is by introducing essentially an interim phase to handle this uncertainty that you have here, with the idea that if you do not disturb the natural dynamic of the system will, even if going through all kind of sequences that are different really and that are completely different depending on the initial condition, they will still jump eventually to what you wanted the system to do. So as long as you do not disturb the system in this phase, then essentially you will be able to continue the execution. So that's what things we did, and we are demonstrating now on this type of motion that I show you, and the details, of course, are some of the papers that we published, and one paper that is also under review on transactional robotics now, and where we also show different type of objects. And here is I show you boxes, and in this case is a pack of rice. This is about I think 0.708 meter per second is about 1 kilo box, and the way at the moment. What we are doing, at least in this type of work, is that we use really low impedance control with really low gains. So even if you have this kind of impacts, there's no problem in handling this because the human is in the loop and you are capable of controlling the robot, even if the robot hands are not really following carefully the position of this tracker that you see one of the students is holding. But once you then record the motion of the real robot, then we can essentially create this extension, as I was mentioning before. This is for the position and the velocity and also for the force. And then we have essentially a way to then track that motion of the real robot now with high gains without having this issue that I was showing at the beginning. We're trying to apply a standard trajectory tracking controller. So if you want to have more details, it's really in this paper, there's an online version already available. But the message here, and I'm just looking at time now, is that we show that by having this new form of controller with this interim mode, which is this proposed approach, essentially we go through this type of impacts you saw, even if you have a mismatch, so then you still impacts before and after, without essentially commanding any big jump in the velocity that you would have, for example, if you would not use this type of strategy with reference spreading, or if you would use the reference spreading approach where you just change the controller only once after an impact occurred. We also compare with another approach, which is also sometimes, I think, used in practice to essentially removing the velocity feedback. And we saw that indeed also removing the velocity feedback before and after the expected impact, it's a possibility. But at the same time, we found it extremely, not robust, at least for manipulation purposes. So this is the typical, a plot, and again, and I don't have the time to go into the details, so I encourage you to read the paper more for details. But essentially, we saw that in the proposed approach, except for the fact that you have a slightly an impact detection phase, where indeed there's a sudden change in the velocity of the system with respect to the reference. Therefore, you have sort of a small spike in the force that you command because there's a large error building up. But after detection of the impact, essentially we have a phase that is a particular intermediate phase where velocity feedback is disabled, but we still have feedback, and we then transition from the pre-impact trajectory to the post-impact trajectory. And this phase is of limited extent, for example, with respect to one phase where you will just disable the feedback before and after, because without having any triggering. So yeah, we are essentially now in our experience, we can clearly see that there is an advantage of using the strategy we're proposing, but we're sort of moving. We are curious, of course, to interact with other researchers to see also what their experience in trying to implement the same strategy. But this is more or less what I wanted to say, at least in terms of trajectory tracking. And I want to finish the talk here mentioning a bit what we are exploring with post-impact velocity prediction. This is an example, from Amazon Robotics LinkedIn post, which is showing what people sometimes call a virtual replica or digital twin, right? Of this idea that you have a real robot, you have a one done with computer graphics. They're clearly visually stunning, but the thing is that when you look at physics interaction and simulation, it's really impossible to reproduce all kind of oscillations that are happening, plus all kind of things with the friction and the soft interaction. So and the question is, okay, how can we combine the two? What should we use, especially for predicting the behavior of the system? So we have done we started in 2017 working, in this case is a work that I've done with Sapadua, where we took just like, for example, this is a lightweight robot arm for KUKA, right? And we essentially just smashed against impacted a surface, planar surface, vertical surface, and we tried to see, okay, can we still use rigid body models and get an idea where the system velocity will jump depending on the configuration and the impact configuration and the anti-impact speed. Can we predict the post-impact speed somehow? We did it with the KUKA paper. We have a paper now that is under the second review on robotics automation letter with the Franca robots to do the similar things with more further result. Also, we discovered that we can include certain effects of the motor dynamics and the low-level torque controller to get a good estimation. But what I want to mention is in general is that we have this is a typical way that we think about this problem. Where model A is a robot where it has a flexible joint and flexible contact, and you can go to a model where you still have the flexible joint, but the contact becomes non-smooth. So it's just impact law type of thing, so a non-smooth model. And you can further reduce where you essentially consider that the links, the transmission between the motor and the joints is rigid, and the contact is also rigid. So this is just a simulation example. You show you that essentially these vibrations that are induced by the softness of the contact and also of the oscillation due to the link, somehow they are a higher order dynamics with respect to the rigid robot that is this model C, as long as you have the right inertia in the model C. So this is really typically what will happen, and also I will show you in a second on another slide where you see these models. We are getting confirmation that we can still use rigid robot models as long as we know the right inertia to place on the links. And in one of the latest paper we have we really show that it's also important to know the low level joint torque gain that you have on the actuators to do so. But if you do so, then you have a fairly good idea where the system will jump, and then you can essentially use this information to create, for example, references to generate motion plans. Because one thing is, okay, you can do demonstration and then you sort of record this jump. You get it from motion. This is something that we have been doing. But the vision here is that to use fully model-based models to be able to pick up boxes and things, assuming to know the inertia of the boxes, and have these type of analytical models validated with the experiments, where what we care is really essentially figuring out what is this gross jump, so that we can generate post-impact velocity references afterwards and then stabilize them. And here's an example of what we get on real experiments, for example, on this Franca robotics arm, right? Where essentially this is a position, the black one, and then we show that essentially, the velocity will, once there's robot will impact, we will have all this oscillation, typically from the flexibility of the motor. The oscillation will depend on the particular configuration and the particular type of surface you're impacting. And you can estimate this light blue line offline after you look at the data. And we are showing that you can, in this way, compute sort of an equivalent post-impact speed of the rigid robot. And we are able to show that we can actually compute this point analytically from an equivalent rigid robot model. So that's what we are doing at the moment. And we are getting sort of confirmation that, if you have the right inertia, which is here, I mean, more detailed in the paper, but somehow you can say, okay, if this was the before impact and this is the post-impact velocity, we see that as long as you compensate correctly for the inertia, you can get pretty decent estimation of where the system will look like. So meaning that you could trust this kind of impact models to then generate plans. And then I show you very briefly, we can have ways of stabilizing this type of motions. I see that I have a few minutes, and then probably there's a few questions coming. So I just want to mention very briefly that we are also, expanding this idea with this idea of vector fields, I would say, or dynamical system, if you're familiar with the work of Ode Billard, where the idea is that we have vector fields before and after impact, and we match these vector fields based on the impact dynamics. Okay, and so we can actually do all these things, not just with the trajectory, so not the trajectory tracking, but also in this context. There are a few papers of students of mine, Jari and Van Steen, on this topic, and where we show that indeed you can have an intermediate phase where things go, quite well, you don't know, but after this intermediate phase, you actually stabilize and you start following. I think there's an animation here, yes, like this. So there's a phase at the intermediate, but then, and this red and blue means the before and after. And this is completely now time invariant strategy, but then having still these benefits of respecting the dynamics and not really, even at high gains, not really putting a lot of requests to the end effectors. Lots of plots, but here that's not important again. So you can get this type of behaviors where that is robust, even if the planning has been done, and I show you it again in a second, even if the planning has been done, assuming that the box was there, even if the box is tilted and rotated, these things, because of this robustness to this reference spreading, you can still achieve robustly this motion. And we are now, in the process of also showing that this can be also implemented on real robots, but we don't expect big issues, but okay, still it's interesting to showcase. And then, okay, here I want to skip this part. It's not essential for the time being. Okay, with this, I think I want to conclude the topic that I did not cover. We are also look at the aim-aware collision monitor. We'll discuss this more at ITRA in Japan. We'll be there to present this type of research. We also done with a group in Munich, and also, I mean, we are exploring that we are also saving this data in a whole database, the TUE, to sort of also make it available for other researchers that are interested in validating impact models. And everybody's is welcome to contact us. And if you have experimental work data with robots, we are happy to sort of include this type of data for the community later on. Special thanks to a lot of students to make this happen, of course, PhD students, master students, a lot of the people that work with me in the last 10 years. And yeah, this is sort of a take-home message, our philosophy is really still using rigid link multi-body dynamics with hard contact, exploring really the difference between reality and physics in the engine simulation in order to make it possible. And then, there's still need for designing robots that are meant for collision. That should be, damp oscillation, be easy to maintain. So this is something that I'm really exploring with some groups here in Europe. And indeed, also increase the effort in experimental validation, really to show that, that we have indeed this whole approach is effective, and you can have really effective post-impact velocity predictors that are essential then for being able to have very good planners. For this, I think I want to thank you all for your attention, and if there are questions, I'm happy to take it.
Hey, thank you very much for the talk. So I will be monitoring the questions. You can type in the chat or you can raise your hand, and I will be monitoring that basically from the audience. So if you have a question, raise your hand if you want to speak up, or you can type your questions in the chat as you prefer, basically. I will be checking on the situation.
Thanks for the great talk. I was wondering if you have looked into like stability analysis, so maybe coming up or calculating region of attraction of controllers through impacts. So how can we come up with formal guarantees about?
Yeah, so that's exactly what indeed I didn't spoke about, but I mentioned that you have this linearization, and so indeed you can assume that is at least locally, you can use this linearization or positive homogenization to have an idea of if the whole controller is attractive by the nominal trajectory. So we have indeed one article. This is more in the transaction of automatic control, where we show that at least if you have single impacts, the whole idea can be used to show that indeed you have a local asymptotic stability to the trajectory. We haven't done it yet for simultaneous impacts.
Yeah.
If you ask me how I would do it, is through this positive homogeneous first order approximation I was mentioning. I have to admit that I parked that sort of theoretical line just because of lack of time. I would love to work with this. It's just that I am really in a rush to make sure to demonstrate this on real robots. And my latest, my ambition is really also moving on planning as soon as possible, because I think it's getting ready to, once you see vision and you estimate objects and you have an idea of the weight, these things that we have built can be really used in this context that I was mentioning. But then the theoretical part is also important, but I'm sort of putting aside for the moment, because I'm a human being, I cannot do everything. But the whole things at the beginning, especially when I was here, and my background is really on control, was on looking at stability. But the regional attraction is also quite big. People think, oh, this is a linear system. No, it's actually very big. So it's like a half a second, sometimes mismatch is still fine. There's no really a big issue there. At least this is my experience. I hope this answers your question. Cheers.
Yeah. Which year was this paper? I would like to take a look.
2017 or 18. I can give you, if you send me an email later on.
Yeah. Okay. Yeah. Okay. We'll coordinate that.
But this is not the robotics literature, it's really on control literature, transaction, automatic control.
Yeah. Thank you very much.
Okay, thank you, Shivesh. We have other questions from the audience. You can also just unmute yourselves. Yeah, Johannes.
I would have a question.
Sorry,
I missed most of the talk, but I think probably this question was anyway not answered. How much do you think, like from a academic point of view, this is all extremely interesting. How much of a truly limiting factor on the industrial side do you believe this, like coming to a stop, making contact, and then going on? Do you really see like an urge from that side, or are we still
if you're talking about
slowly moving?
If you talk about
Overall.
logistics, the urge. In logistics, you have a cycle time of 4 seconds, 5 seconds. So
5 seconds, yeah.
5 seconds, 4 seconds bringing boxes, yes. And in most of the things that happen, I mean, if I talk with also, because we have this connection with the industry locally here, right?
Yeah.
They really say, well, we evaluated a solution, but it's too slow, right? If a robot takes, I don't know, 30 seconds to pick up a box, then there's a use case, a business case is gone, right? So if you want to get at the level of performance of humans, of course, there's the usual trick. Automation, I structure the environment, and then you go millions. So if you can do automation, classical automation, you should go that way, right? And also the company work will be like a depalletization. They will go and they have a system that pick up everything from the top with an enormous suction cup, put it on a conveyor, then they do simulation. I mean, the footprint is enormous, but there are a lot of drivers now that are, they are making it really hard to go that way. The time, the cost of the system, the fact that, now that there's an environmental push to make boxes, I mean, really light, not really structured, so you cannot even pick them from the top. I honestly, whenever I talk with industry, I have the impression they are really interested, but before convincing them, you have to show a demo, which is more or less what we are working on, and it's all together, and you have to put a lot of pieces. So what I'm saying is that many people, I think, are trying this. I have one way, and I think for the control part, we have a good strategy. But there are all way more other bricks that we need to put together in order to get there. But I think the problem is real, and is really in terms of cycle time. That think of moving things in 4 seconds. That's what people want to do from 1 meter distance. It can be luggage, can be boxes, but that's and then if you want to be fast, well, we save energy not by lifting. We really exploit contact and so on and so forth. And I'm not saying that you should always use impacts. And so and what I'm proposing here anyway, it's also for contact rich in the sense that zero speed transition is also an impact. So I'm not excluding that you can transition and robustify things even at contact speed. So I'm looking actually at both. I hope this answers your question, Johannes.
Yes. Thank you.
Okay. If there's no question in the audience, then I have a question while waiting to see if there's more questions for the audience. It's about the, it's a bit unrelated in the sense that it's about the end effector that you're using for these impacts. So is that something that you actually looked into, or is this, let's say, I suppose there is some relevance in that sense, but is this something that you have actually looked into?
We are looking at, I don't remember it. I think in one of the latest paper or in the future paper we'll also discuss. So indeed, it's important to have the right hardware in a sense. So, and if you think of how we are structured, we have a skeleton and we are covered with muscles and fat. And those two things really help a lot in damping oscillations. So in the video that you show with the dual arm system, we design custom end effectors that are made of silicon. So they have a core that is 3D printed in plastic, and then there's a silicon top. And indeed, this actually allowed to use, for example, this panda that are really not meant for what I showed. If without those, if you would impact, for example, a rigid surface, maximum speed you could reach before triggering events are 0.2 meters per second. If you add this, of course, it takes more time for the force to build up. So we managed to get these speeds like you saw, 0.7. In general, it's really good to have, in any case, a gripper that has also tangential grip. Because if you have to pick up an object, if you use just plastic, this thing will just slide. So there's two, indeed, it's worth investing in developing end effector that, damp energy in the direction of the impact, but also provide enough grip. We are also building and designing new end effectors, especially for the dual arm depolitization in these days. But we haven't published yet, but we are looking into it. Yes, it's definitely interesting and relevant.
Okay, yeah, because that's what I thought, like that. It definitely, I saw that you have made definitely hardware modifications, but that's definitely the contact point of with the impact, right? So that's what I thought. Okay.
Yeah, in the future we envision that you probably have to cover things with some form of skin again because tangential friction you need to know to have in order to move things around.
For sure. Okay, thank you. Do we have any last questions from the audience? I will wait a few seconds before closing the session. Okay, I will take that as no more questions. So thank you again, then Alessandro, for the great talk. We will not post the video immediately. We'll do some editing, but should be out in a few days.
Thank you very much again for the invitation.
Yeah.
And
okay.
for the time for everyone being here.
Yeah.
Thanks a lot.
Thank you everyone for attending.
Thank
Bye.
you. Bye-bye.
Bye.
Bye.